Hello everyone and welcome back. Today we're going to start looking at permutations, combinations, and ways that we can use these together. A permutation is a way that you can arrange a set of n distinct objects in a specific order without repetition. A couple key things here: if we're talking about anything where we have a specific order or where the order matters, then that means we're talking about a permutation. Also, we can't have any repetition. We will ultimately be able to count things that have repetition, but for now when we say a permutation, we're talking about organizing objects, distinct objects, so that means there's no repetition, and we're organizing them in a distinct order, a specific order. So let's take a look at this example that we have right here. Suppose that we have 10 paintings, but we only want to hang 7 of them on the wall. How many different ways can we do this? There are a couple different ways you can think about this problem. The way that I like to approach it is I imagine that I have my 7 paintings. So I have like 7 spots. 1, 2, 3, 4, 5, 6, 7. Okay. And when it comes to hanging the first painting, I could hang any one of the 10 paintings that I have. Now once I've hung the first painting, when I get to the second one, there are now only 9 paintings remaining. And that's because I don't have once I've hung the first painting, now I'm down to 9. I can't use the first painting twice. When I get to the third painting, there are 8 options, and then we have 7, 6, 5, and 4 options. Now, this means these are sort of like the branches on my tree. So if I want to figure out how many ways that I could hang these 7 paintings, I want to take the product. So I want 10 times 9 times 8 times 7 times 6 times 5 times 4. Now this should look kind of familiar, or at least maybe a little bit suspicious, that we're multiplying in order, starting at 10, the number of paintings that we had, and then we went down to 4 for some reason. So take a look back up at the notes right above this problem. Recall that a factorial is given by the product of n times n minus 1 times n minus 2, etc., all the way down until we hit 1. What it looks like we have here is almost 10 factorial. In fact, what we have is 10 times 9 times 8 times 7 times 6 times 5 times 4, and then we stopped. So if we were to write this as 10 factorial, so 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, what we did is we divided out by everything after 4. So we divided out by 3 times 2 times 1. So what we had was 10 factorial in the numerator divided by 3 factorial in the denominator. Well, where did we get 3 from? Why is it that we had 3 terms that we didn't include in the factorial? That's because if we're only hanging 7 paintings, then we should have 3 left over. And so our formula, if we want to count using a permutation, we can always do this using like these little, buckets like I've done at the beginning here. Or we can go ahead and approach this using the definition of a permutation, which is given below. So our definition, the permutation of n objects into k is going to be given by n factorial divided by n minus k factorial. And so in this example, we have n equals 10. There are 10 paintings. K is how many paintings we are keeping, so we have 7. And so we have 10 factorial divided by 10 minus 7 factorial, which is 10 factorial divided by 3 factorial, exactly what we saw before. And the total number of ways that we can hang our paintings then would be given by, oh, it looks like I didn't actually multiply it out. So this could be given by 10 factorial divided by 3 factorial, which is 604800. So 604,800 different ways that this can be done, that we can hang our paintings. In the future, if we're dealing with a permutation, so that means we have distinct objects and the order matters. And so if we're hanging paintings on a wall, the order that we hang them matters. Otherwise, we have a different arrangement. So if we're dealing with a permutation, we can always use this formula from here on out. Or you can think of it as like we did at the beginning where we imagined how many options do we have for each step along the way. Let's take a look at this second example now. We have a club that has 52 members and 21 pledges. We have to pick a president, vice president, and a secretary from the members. So out of the 52 members, we will be selecting a president, a vice president, and a secretary. And we have 21 pledges, and from the pledges, we will have a pledge chairman and a pledge vice chairman. How many different ways can the 5 officers be selected? Well, the first thing we want to figure out is this a permutation or is this something else? Now, I know that we don't have a distinct order here, but if I select 3 people and I assign one of them the job of president, one of them vice president, and the other one secretary, then that is assigning an order to the people. So when we're dealing with a permutation, this will count if we have an order like we did with the paintings, or equivalently, you can think of this as having like a title or a rank, anything where you are assigning a specific duty to people, and that duty is different from person to person. Then that's also considered like an order. So if you have a title or a rank, that also counts. So let's look at first the different ways that we can select the president, the vice president, and the secretary. And so we will select president, vice president, and secretary. We have 52 members total, and to select the president, vice president, and secretary, we will be selecting 3 of them. And so we want the permutation of 52 into a group of 3. This means that if I have selected, Johnny, Sarah, and Sally, then that group of 3, the order matters. And so I'm counting, if Johnny is president, Sarah is vice president, and Sally is secretary, that counts as a different ordering than if Sally were president, Johnny were vice president, and Sarah were secretary. So this is counting the different arrangements we can have, even if it's the same group of 3 people. How many ways can we select the chairman and the vice chairman? So selecting the chairman and the vice chairman, we have a permutation. There are 21 people total, 21 pledges, and we are selecting 2 of them. There are 2 positions to be awarded. So we want the permutation of 21 into 2. Now these 2 numbers have to interact, and they will be multiplying, because you can think of this kind of as branches along a tree. So first we are selecting our president, vice president, and secretary, and then we select our chairman and vice chairman. And so they're branches along a tree, and so we need to multiply as we go along the branches. So let's see. For the president, vice president, secretary, we have as factorials, we would have 52 factorial divided by 52 minus 3 factorial. And then for the chair, vice chair, we have 21 factorial divided by 21 minus 2 factorial. And so let's see, we'll have 52 factorial divided by 49 factorial times 21 factorial divided by 19 factorial. And we could go ahead and put this in our calculator right now, but we can always simplify our factorial fractions a little bit. Let's think about 52 factorial divided by 49 for a moment. So I'm going to kind of do this on the side up here. So let's just sort of consider scratch thought for a moment. I want to simplify 52 factorial divided by 49 factorial. Well, 52 factorial says 52 times 51 times 50 times 49 times 48 ... until we get down to 1. Well, 49 factorial in the denominator says 49 times 48 times 47 ... until we get down to 1. Notice that once we hit 49, everything that came after 49, so 49 factorial, was in the numerator and the denominator. So that means that in our fraction 52 factorial over 49, we are simply left with 52 times 51 times 50. Once we hit 49, that is divided out by the denominator. So let's come back to the problem we were working on. 52 factorial over 49 factorial will simplify to be 52 times 51 times 50. And similarly, 21 factorial will simplify to 21 times 20. We don't hit 19 because the 19 gets divided out by the 19 factorial, and everything after 19 is also divided out. And so now we can just multiply this out using our calculator, and we end up with, 55,692,000 different ways that we can select a president, vice president, secretary, and a chair and a vice chair from the students that we have available. Okay, so I want you to get used to taking a factorial and simplifying it like we did here. I also would like you to get comfortable reading a problem and figuring out how to represent it as a permutation or later on as a combination. All right, that's all for now.